Welcome to Biogas Basics. My name is Jürgen Kuber, and this is the third part of the mini-series about microbial growth in the biogas reactor. In the previous presentation, I discussed hydrolysis kinetics, which are often the rate-limiting step of the AD process. During normal operation, process steps further downstream, like acetogenesis and methanogenesis, do not restrict the AD process. However, there are some noticeable exceptions when the limitation of the methanogenetic phase can be a problem. In this presentation, we discuss the limitations and inhibitions of the methanogenetic stage. There are two methanogenic pathways, the hydrogenotrophic and the acetoclastic pathway. Methane can be made from CO2 and hydrogen or from acetic acid. The acetoclastic are slower growing than the hydrogenotrophic methanogens and more inhibited by ammonia. I will only focus on them for now. Almost all methanogens can make methane from hydrogen and CO2, but not all methanogens can make biogas from acetic acid. Since acetic acid is an important intermediate product of the acetogenic and acetogenic phase, it will accumulate if it is not consumed by methanogens. Let's address one common misconception head-on. Acetic acid does not inhibit the production of methane. This figure shows the percentage of the maximal growth rate of methanogens as a function of acetic acid in its protonated form. High concentrations of acetic acid do not cause a slowdown of growth. There is an indirect impact via the pH value, but I will talk about this in the next slide. The functional relationship between acetic acid concentration and growth rate is a monod kinetic as shown in this figure. The substrate in the monokinetic is acetic acid in its protonated form. The dissociated form, the acetate, does not impact the growth rate. For the microorganisms, only the uncharged form is relevant. We will see this behavior again later when we discuss ammonia inhibition. Acetic acid is a weak acid and can dissociate. It can either be in the acid form, meaning it is protonated, or in the acetate form, i.e. unprotonated. The dissociation reaction is described by an equilibrium reaction. At 25 degrees Celsius, the equilibrium or dissociation constant is 10 to the power of minus 4.75 moles per liter. The negative decadic logarithm of the dissociation constant is called pKa value. The pKa value is temperature dependent. At 38 degrees it is 4.93. When the pH value is identical to the pKa value, the dissociated and undissociated form are in a 1-to-1 ratio. The undissociated form dominates when the pH is lower than the pKa value and is more prevalent when it is high. So, when the pH in a biogas reactor is 7, most of the acetic acid is in its biologically inert acetate form. As a rule of thumb, when the pH equals the pKa, the ratio is 50 to 50. If the pH is 1 unit away from the pKa, the ratio is 90 to 10. At 2 units 99 to 1, at 3 units 99.9 to 0.1. In a biogas digester with 38 degrees Celsius and pH 7, roughly 99% of the total acetic acid are in the biologically inert acetate form, and only 1% is biologically active. When we measure total acetic acid, for example with a GC, we measure the sum of acetic acid and acetate. We now switch the abscissor value from the protonated acetic acid to the total acetic acid. The dependence of the growth rate on the total acetic acid concentration is pH dependent, as the pH influences the dissociation equilibrium. According to the monod kinetic, the lower the pH, the faster the acetoclastic methanogens will grow. At first glance, this contradicts experimental evidence, but the pH does not only influence the dissociation equilibrium of acetic acid, but of a few other important molecules in the biogas process. Further, an unfavorable pH also has an impact on the Mumax or doubling time in free growth. If the pH gets too low, the methanogens slow down their growth rate, not because of limitation or inhibition, but simply because of unfavorable pH conditions. Methanogens rely on proton pumps for energy generation, and they are severely impacted by a low pH that leads to an accumulation of protons outside the cells. This figure uses a monoconstant of 70 micromoles per liter. This is an average value. Many microorganisms can be grouped into generalists and specialists. This is not only true for methanogens. Generalists have a higher growth rate, but also a high monoconstant. The monoconstant is the concentration of substrate at which the growth rate is half the maximal growth rate. The higher the monoconstant, the more substrate must be present to achieve high growth rates. Specialists, on the other hand, have lower growth rates but also lower monod constants. They outcompete generalists at low substrate concentrations, or high residence times in the CSTR. Generalists are better in a changing environment or at lower residence times. Methanosacina are typical generalists with minimal doubling times of around 7 hours. Methanogenesis are typical specialists with doubling times of 40 to 100 hours, but lower monoconstants. The monoconstants of acetoclastic methanogens measured for generalists are around 120 micromoles per liter. For specialists, this number can drop to 20 micromoles per liter. Normally, we do not know the microbial composition of a biogas digester, so it is difficult to make exact predictions of the acetic acid concentration in a digester, but we can use average values to explain the concept here. Let's investigate an example. A biogas digester with 30 days residence time has a pH of 7. The methanogens in the digester can double every 5 days in free growth. The monoconstant is 70 micromoles per liter. What acetic acid concentration can we expect in the digester? We know from the first presentation in this mini-series about microbial growth in AD reactors that the actual doubling time or equivalent growth rate in the digester is linked to the hydraulic residence time. The growth rate μ is the inverse of the residence time. We can calculate μ max from the doubling time in free growth. It is ln2 divided by the doubling time in free growth. The ratio of μ and μ max is around 24%. We can now project the 24% ratio onto the pH 7 curve and read the concentration of total acetic acid on the abscissa. We can expect an acetic acid concentration of 150 mg per liter. We can repeat the exercise for different pH values. At pH 7.5, we would expect 500 mg total acetic acid per liter, and at pH 8, 1500 mg per liter. What can we learn from this slide? Acetic acid will always be present in steady state, and it will accumulate at higher pH to allow the methanogens to keep up the growth rate required to stay in the digester. A high residence time in the primary digester can help to alleviate stress caused by high pH. We will see similar behavior when we talk about ammonia inhibition. During a process change, or a feed shock, acetic acid will accumulate, which will help the methanogens to temporarily grow faster and overcome growth restrictions caused by the shock. According to this figure, a low pH would allow the methanogens to grow faster, which is not what we see in reality, especially during an acidification of the digester. That is because acetic acid is not the only volatile fatty acid produced in the biogas reactor. There is also propionic acid. Propionic acid is toxic for methanogens. The inhibition kinetic can be described with a non-competitive inhibition approach. We multiply a factor Ki divided by Ki plus the concentration of the undissociated propionic acid to the monokinetic. When the propionic acid concentration is 0, the term is 1 and no inhibition occurs. The inhibition constant Ki is 0.97 millimole per liter. At this concentration, the growth rate has slowed down to 50%. At 4 millimole per liter, or roughly 300 milligram per liter, the growth rate is roughly 20% of the uninhibited growth rate. The concentration here is for the undissociated propionic acid. If we want to investigate what happens to the growth rate when propionic acid accumulates in the digester, we need to discuss the impact of acid accumulation on the pH value first. Let's plot the relative growth rate, μ over μ max, over the total acetic acid concentration. Unlike in the last two graphs, here the concentration on the abscissa is the total acetic acid concentration, which is the sum of acetic acid and acetate, and not just the undissociated form. The total acetic acid, meaning the sum of dissociated and undissociated acetic acid, is measured in a volatile fatty acid analysis. The conditions for this thought experiment are a pH of 7.1, and neither acetic nor propionic and no other volatile fatty acids are present. The system is buffered by the presence of 2 grams per liter ammonia and ammonium and a dissolved CO2 concentration in equilibrium to a partial pressure of 1 bar CO2. The dissolved CO2 is in equilibrium to bicarbonate and carbonate. All dissociation equilibria are pH dependent. I will make a separate presentation about the ammonium carbonate buffer and how to calculate pH values. As the total acetic acid accumulates, the pH in the system will go down, and the dissociation equilibrium will shift slightly from the inert acetate to the bioavailable acetic acid form, leading to a slightly increased growth. This effect is on top of the monokinetic, where a higher acetic acid concentration leads to a higher growth rate. Now what happens if propionic acid is present? On one hand, the pH should drop, and acetic acid should become more bioavailable, speeding up growth. On the other hand, propionic acid is toxic, and when the pH drops, it becomes more toxic. This curve shows the growth rate when 2 grams per liter of total propionic acid, the sum of propionic acid and propionate, are present. Now we can see a decline in growth rate when acetic acid accumulates. The presence of propionic acid makes the acetic acid appear to be toxic as well. To be clear, This is not because acetic acid is actually toxic, but purely because it lowers the pH and makes the propionic acid more bioavailable. The effect intensifies when we increase the total propionic acid to 4, 6, 8 and 10 gram per liter. We can visualize the effect of the acid accumulation by plotting lines of constant pH into the graph. We select a constant pH, then for every acetic acid concentration, we can calculate the propionic acid concentration from the ion balance, and finally, we calculate the growth rate as a function of acetic and propionic acid. When no volatile fatty acids are present, the pH is 7.1. Once acids start to accumulate, the pH will drop. These are the lines of constant pH for pH 7 to pH 5.8 in 0.1 intervals. Let's have a look at the pH 6.8 line. When no propionic acid is present, we will need to add 6.7 gram per liter total acetic acid to the digestate to bring the pH to 6.8. At 2 grams per liter total propionic acid, 5.1 grams per liter total acetic acid are required. At 4 gram per liter total propionic acid, it is 3.5 gram per liter acetic acid, and at 6 gram per liter propionic acid, it is 1.9 gram per liter. At low pH, the mu-max factor will decrease as the methanogens are inhibited. This effect is technically independent from the acid inhibition and is caused by a reduced functionality of the proton pump that is used by methanogens in the production of energy. We know from the first presentation in this mini-series that the growth rate in a steady state, CSTR, is linked to the hydraulic residence time. For example, if the microorganisms have to grow at a relative growth rate of 60%, they can grow at no propionic acid and 1.33 gram per liter total acetic acid, or at 2 grams per liter of each total acetic and total propionic acid, or at 8 grams per liter total acetic acid and 2 grams per liter total propionic acid. The last point is an unstable solution. Let me explain what unstable means. In a steady-state bioreactor, the concentration of the substrate, in this case the acetic acid, will always fluctuate slightly, even in steady state. Normally, when the substrate concentration increases, the growth rate will increase as well, and more microorganisms will be produced, which will in turn consume more substrate. And when the substrate concentration drops, the growth slows down, leading to a lower biomass concentration, which consumes less substrate, allowing the substrate concentration to recover. This creates a feedback loop, which keeps the biomass concentration stable. However, this feedback loop only works if the slope in the growth rate over substrate concentration diagram is positive, or left of the maximum. When the slope is 0 or negative, the feedback loop does not work, and the reactor becomes unstable. It enters a self-reinforcing inhibition. In the biogas industry, this is called acidification. We can identify the acidification territory by connecting all maxima on the curves of constant propionic acid. In theory, the acetic acid concentration can be unlimited when no propionic acid is present. At 2 gram per liter of total propionic acid, the reactor can sustain up to 4.7 gram per liter total acetic acid. At 4 gram per liter propionic, it is 3.3 gram per liter acetic acid, and so on. Again, we see how propionic acid limits the amount of acetic acid that can be present before the reactor becomes unstable. If an acidification occurs, feeding must be reduced or stopped. The reduced feeding lowers the required growth rate. Remember, the growth rate in a steady state, CSTR, is 1 over residence time. In the worst case scenario, the propionic acid concentration stays constant. Follow the line of constant propionic acid to the new growth rate. For example, if the system was at 2 grams per liter total propionic acid and at 8 grams per liter total acetic acid and requires a relative growth rate of 60%, a reduction of feeding to a required growth rate of 40% will lower the total acetic acid concentration to around 0.9 grams per liter. The addition of a strong cation, for example sodium or calcium hydroxide, can also help. However, because of the ammonium carbonate buffer, large amounts of cations are required to have a significant impact on the growth rate. The addition of cations should only be used in addition to a reduction of feeding and not as a substitution. Now let's have a look at the impact of ammonia inhibition. Before we start with the impact of ammonia on methanogenic microorganisms, I show a quick recap of some basic water chemistry. Total ammonia nitrogen, or TAN, is the sum of ammonia and ammonium. In the biological context, only the uncharged ammonia is relevant, sometimes called free ammonia. The charged ammonium is biologically inert, but it has an impact on the charge balance of the digestate and thus the pH. Traditionally, the mass concentration of total ammonia nitrogen is given as gram per liter nitrogen, so with a molar mass of 14 gram per mole. Ammonia and ammonium are in equilibrium. Ammonia is a base and it increases the pH value, but ammonium is its conjugated acid and we can describe the equilibrium with an acid dissociation. Ammonium meets the definition of a Bronsted acid. It can donate a proton. Combining the first two equations allows us to express the concentrations of ammonia and ammonium as a function of the pH value, the dissociation constant, and the total ammonia-nitrogen content. The dissociation equilibrium is temperature dependent. The pKa value decreases when the temperature increases. The dissociation constant, or pKa value of ammonium, is often given as 9.25, which is the value at 25 degrees Celsius. But at 37 degrees Celsius, the value drops to 8.89, and at thermophilic conditions, at 55 degrees Celsius, the pKa value is 8.41. We can see the impact of temperature on the dissociation equilibrium in the figure. The abscissa is the pH value, and the ordinate is the ratio of ammonia to total ammonia-nitrogen, and the corresponding ratio of ammonium to total ammonia-nitrogen. The bold line is the percentage of the bioactive ammonia, and the dashed line is the percentage of the inert ammonium. The red line is for thermophilic conditions at 55 degrees Celsius, the blue line for mesophilic conditions at 37 degrees Celsius. Remember, when the pH is the pKa value, the dissociated and undissociated form have the same concentration. At the pKa value, the dashed and bold lines intersect. Now let's take a biogas reactor at a pH 7.5. At 37 degrees Celsius, 3.9% of the total ammonia-nitrogen is in the bioactive free ammonia form, and 96.1% are biologically inert ammonium. If we increase the fermentation temperature to thermophilic conditions at 55 degrees Celsius, the free ammonia percentage increases to 10.8%. Without an increase of the total ammonia concentration, the ammonia becomes 2.8 times more active. Now let's go back to the biological implications. Ammonia is both a substrate and an inhibitor for methanogens. They need a small concentration for growth, but at higher concentrations, the ammonia quickly becomes inhibiting. The mathematical description of this correlation is the Haldane kinetic. The first term is similar to the monod kinetic, and then we multiply a term Ki over Ki plus free ammonia to the kinetic. At no or low ammonia concentration, the inhibition term is 1, but as the ammonia concentration increases, the term becomes smaller and eventually dominates the monoterm. The nitrogen inhibition kinetics were researched in the 1980s and 1990s. Some of the best papers were published by the groups around Birgitte Aring and Irini Angelidaki at the DTU in Copenhagen, and by Claudia Gallert and Josef Winter, then at the University of Karlsruhe. I use the following parameters here, but those parameters vary slightly from source to source. Generally, I use the formula to show the mechanistic correlations of important factors in the AD process. The formula should not be seen as 100% accurate predictions. We talk about highly complex biological systems after all. The figure shows the relative growth rate of acetoclastic methanogens as a function of free ammonia-nitrogen for mesophilic and thermophilic microorganisms. Interestingly, the thermophilic methanogens are more tolerant towards free ammonia-nitrogen than mesophils. They have a higher inhibition constant. That seems to contradict the common observation that thermophiles are more prone to nitrogen toxicity than mesophiles. The reason for this is the temperature dependence of the dissociation constant we discussed in the previous slide. So, some ammonia is good, but too much is bad for the methanogens. Ammonia is a base, and increasing its concentration will increase the pH. A higher pH shifts the dissociation equilibrium from the inert ammonium towards the toxic ammonia, but it also shifts the acetic acid to acetate. How does it all work together? We start by plotting the growth rate as a function of the total ammonia-nitrogen, TAN. The previous slide showed the growth rate over the free ammonia, but this figure uses the total ammonia-nitrogen, so the sum of ammonia and ammonium on the abscissa. The total acetic acid concentration is 0.5 gram per liter. As the total ammonia increases, the pH increases as well. We can mark the pH values on the curve, starting with a pH of 6.7 and going all the way to pH 7.6. Next, we plot lines of constant total acetic acid. We add lines at a total acetic acid concentration of 1, 5, and 10 gram per liter. At constant total ammonia-nitrogen, the microorganisms can grow faster when the acetic acid concentration increases. We can connect points of constant pH along the lines of constant total acetic acid to see the impact of total ammonia-nitrogen and total acetic acid on the pH value. These are the lines for 0.8, 7.0, 7.2, 7.4, and 7.6. Okay, now we have a complicated diagram. How to read it? Let's look at an example. A biogas reactor has a pH of 7 and a residence time that requires a relative growth rate of 30%. Remember, in a steady-state CSTR, the growth rate is the inverse of the residence time, at least for the primary digester where the inflow does not contain microorganisms at elevated concentrations. This is equivalent to the doubling time of all microorganisms is ln of 2 times the hydraulic residence time. A fixed residence time requires a fixed growth rate. At a total ammonia concentration of 1.5 gram per liter, the pH will be 7.0 and the acetic acid concentration is 0.5 gram per liter. When the tan increases to 2.6 gram per liter, the total acetic acid concentration will increase to 1 gram per liter, and the pH is roughly 7.1. When the tan increases to 5 grams per liter, the acetic acid must increase to 5 grams per liter to allow the acetoclastic methanogens to keep up the required growth rate. And at 6 grams per liter tan, the required total acetic acid concentration jumps to 10 grams per liter. At high total ammonia concentrations, the methanogens must allow higher total acetic acid concentrations in the digester to sustain the required growth rate. The acetic acid also brings the pH down and makes the total ammonia nitrogen less toxic by shifting the ammonia back to the ammonium. But there is a limit to this mechanism. Increasing tan concentrations will require more total acetic acid to be present, and at some point, high acetic acid concentrations will inhibit the acetogenic microorganisms. So far, we only discussed the impact of ammonia on methanogens, but ammonia also influences the acidogenesis reaction of amino acid degradation, the Stickland reaction. At this point, I will show the slide about the CN ratio again. One of the myths in biogas is the carbon to nitrogen or CN ratio. Many AD textbooks recommend a certain window for the CN ratio to avoid nitrogen inhibition or limitation. In reality, the CN ratio is meaningless. Like many key performance indicators in the anaerobic digestion world, the CN ratio stems from the aerobic technology, especially around the aerobic wastewater treatment. In an aerobic cultivation, the yield coefficient is somewhere between 30 and 50%, meaning that 30 to 50% of the carbon in the substrate is converted to bacterial biomass. And bacterial biomass consists of roughly 10% nitrogen, so for every mole of carbon consumed, there must be a certain amount of nitrogen present, or the biomass cannot grow. The yield coefficient of anaerobic microorganisms is 1 order of magnitude lower. Less nitrogen is required per mole of carbon consumed. The AD process is rarely nitrogen limited. There are only a few exceptions to this. Mostly in wastewater fermentation or specific feedstocks like whey permeate that require the addition of some nitrogen. And the nitrogen inhibition is not due to a low CN ratio, but because of high free ammonia concentrations, as we have just discussed. Further, in wastewater technology, usually most or all of the carbon is biodegradable. After all, the aim is to make clean water. For the feedstocks in AD, this is mostly not the case. I talk about organic dry matter degradation rates in my feedstock presentation. Manure has an organic dry matter conversion rate of 40 to 50%, straw has 60%, energy crops have 70% to 90%. Not all carbon will be converted. Adding inert carbon into a biogas digester will influence the CN ratio, but it will do nothing to the nitrogen inhibition. The way to overcome a nitrogen inhibition is not to add more carbon to the digester, but more nitrogen-free water to lower the free ammonia concentration. To conclude, acetic acid is the limiting substrate for acetoclastic methanogens, but it is not an inhibitor. Perceived inhibition during acid accumulation comes from a drop of pH, an increased toxicity of propionic acid, but not from the acetic acid itself. The total acetic acid concentration comprises acetic acid and acetate. Only the protonated uncharged form is bioactive. The acetate is biologically inert. Propionic acid is a major inhibitor to methanogens, again only in the protonated form. Total ammonia nitrogen comprises free ammonia and ammonium. The uncharged free ammonia is the bioactive form and can be both limiting and inhibiting, though the limitation occurs only at very low concentrations and is uncommon. The dissociation equilibrium of ammonium is temperature dependent. The higher the temperature, the lower the pKa value of ammonium and the higher the percentage of the toxic free ammonia. If nitrogen inhibition is a problem, lower the fermentation temperature. The bioavailability of acetic acid, propionic acid, and ammonia is pH dependent, and the pH itself is a function of the concentration of the total amounts of these species. Higher total ammonia-nitrogen concentrations lead to a higher pH, making the ammonia more toxic. When the methanogens are inhibited, they must tolerate more acetic acid in the digestate. Generally, if the pH deviates too much from the 7 to 8 window, it is a sign for process inhibitions, either by volatile fatty acids or by ammonia. This concludes part 3 of the mini-series on microbial growth. I hope you learned something new, and I see you in the next episode of Biogas Basics, where I discuss acetogens and their thermodynamic inhibitions.